As well as the King of Persia, there are a number of fables and anecdotes related to sums of geometric progressions. Most of these are based on the ratio being a half. There's the joke about someone who walks into a bar and says, "I'll have a drink for myself, half a drink for my friend, quarter of a drink for his friend, an eighth of a drink for his friend's friend," and so on, until the bartender interrupts and says, "I understand," then promptly pours 2 full drinks. The Eye of Horus was said to be fractured into multiple parts worth a half, a quarter, an eighth, a 16th, and so on. And Arrow's paradox based on this sequence was even the basis of a romantic scene in the movie IQ, a Hollywood film with Tim Robbins and Meg Ryan, where Meg Ryan says that they can never kiss because to get to Tim, she would have to cover half the distance between them, and then half of that distance, and then half of that distance, and then half of that distance, and it'll take an impossibly long time before she can reach him. The algebra of how we calculate sums of geometric progressions is a little less romantic, although it does involve a few special tricks. We start by writing out our sum algebraically with a plus ar plus ar squared plus ar cubed all the way up to ar to the n minus 1, because this is what the nth term will be. And we'll introduce a variable which we'll call Sn, which stands for the sum of the n terms, and say that these are equal to one another. And so if we multiply both sides by r, we'll have Sn times r on the left-hand side, and on the right-hand side, every term will be multiplied by r. And so now we'll have ar squared, ar cubed, and so on, all the way up to ar to the n. Remember from our index laws that if we have r to the 1, which is just r, multiplying by r to the something else, we just add those indices. So when we multiply r by r to the n minus 1, we'll just have r to the n minus 1 plus 1, which will cancel each other out. And now we'll subtract what we started with, the Sn, from this Sn times r. On the right-hand side, we'll have all of those ar squared terms, and then subtracting the terms in the original sum, we'll have this effect of many of the terms cancelling each other out. All we'll be left with is ar to the n, because remember in that first sum we only went up to ar to the n minus 1, and we'll just be subtracting a, because remember in that second sum everything was multiplied by r. And so now the left-hand side and the right-hand side have only a few terms each, and we can factor out Sn on the left, we can factor out a on the right, and then rearranging we get this very nice compact formula for calculating the sum of a geometric progression. The nifty algebra work here might remind you of working out how to express decimals as fractions. In both cases, we introduced a variable, multiplied both sides, then had this cancelling out effect until we arrived at this very nice sum, which doesn't depend on an infinitely long sequence. And as it happens, we can also express these recurring decimals as the sum of a geometric progression. For example, a third, which is 0.33333 recurring, can be expressed as the sum of the sequence 0.3 plus 0.03 plus 0.003. And so what we have here is the first term 0.3, the common ratio of a tenth, and then the more terms we take, the closer we'll get to that actual expression of a third. As with the sum of an arithmetic progression, we can code the sum of a geometric progression into R in order to help us explore. We'll just need to make sure about all the operations we use. You'll need to use brackets when you're looking at that denominator there so that we're dividing by r minus 1. And remember in the numerator, we're subtracting 1 from r to the n. We're not raising r to the n minus 1. And once we have our sum as a function, we can look at how different values produce different results. With the example of the ratio being a half, where we're adding 1 plus a half plus a quarter plus an eighth and so on, you can see that changing the value of n gradually will bring the sum closer and closer to 2.